Today, we're digging into the engine that powers almost all of machine learning, gradient descent. It's the core algorithm that lets machine actually learn from its mistakes. So let's get right into it.
So you hear about machines learning all the time, right? But what does that even mean? How does it actually work? When a model gets an answer wrong, how in the world does it figure out how to do better next time? Well, the secret is it's not some giant instantaneous leap of logic. It's a process. A machine learns by taking one small, careful step at a time, getting just a little bit less wrong with every single move. Okay, so if it's all about taking steps to correct mistakes, first we have to be clear on what a mistake even is. This brings us to the fundamental goal of this whole thing, making mistakes as small as possible. In machine learning, we measure mistakes with something called a loss function. You can just think of it as a wrongness score. It looks at what the model predicted, compares it to the correct answer, and spits out a number. Big number, big mistake. Small number, you're getting warm. The whole game, literally the entire point of training, is to find the settings that get that loss number as close to zero as humanly or machinely possible. Now, you might be thinking, can't you just use a fancy math equation to find the perfect answer right away? And for super simple problems, maybe. But for the really cool stuff, like the neural networks that power AI today, there's no magic formula. The world of possible answers is just too massive and complicated. We can't solve for the best one. We have to search for it. And gradient descent is our GPS for that search. To really get a feel for this search, let's use an analogy. I want you to picture this. You're a hiker standing on a huge, foggy mountain. Your goal is to get to the lowest point in the entire valley. But you can only see like 2 feet in front of you. What do? You'd probably do the most logical thing, right? You'd feel the ground around you with your foot, find the direction that goes downhill the steepest, and take a small, careful step. That's it. And that simple, powerful idea is the heart and soul of gradient descent. In our analogy, the mountain landscape is the loss function, and the bottom of the valley is the point of minimum error we're trying to find. So our hiker has a basic strategy. Now let's lay out the specific rules of the hike. These are the core mechanics of the algorithm itself. So here's the 4-step dance. 1. You start somewhere completely random. Just drop our hiker anywhere on the mountainside. 2. From that spot, you calculate the steepest way down. 3. You take one small step in that direction. And 4. Repeat. You just do it again and again and again. Each step gets you a little bit lower, a little bit closer to the goal. Okay, but step 2 there sounds a little bit like magic, doesn't it? How does the algorithm, lost in this thick metaphorical fog, actually know for sure which way is the steepest way down? Well, this is where the gradient part of the name comes in. In calculus, the gradient is this amazing tool that, at any point on a surface, points in the direction of the steepest ascent. It points straight uphill. So, if we want to go down, we just do the simplest thing you can imagine. We take a step in the exact opposite direction. It's our perfect compass for finding a way to the bottom. Now, knowing the direction is only half the battle. The other crucial piece is the size of our step. This is controlled by a setting called the learning rate. Is our hiker taking tiny, shuffling baby steps, or are they taking giant, confident leaps? This choice is absolutely critical. And this table just lays it all out perfectly. If your learning rate is too small, our hiker takes these microscopic steps. They'll get there, eventually, but it might take forever. On the flip side, if the learning rate is too large, our hiker takes a massive leap, flies right over the bottom of the valley, and lands halfway up the other side. They could even end up farther away from the goal. So you're always trying to find that just right, Goldilocks learning rate to get to the bottom efficiently. So we've got our rules for the hike, but it turns out there's more than one way to get down a mountain. Depending on the terrain, or in our case, the data, we can use a few different strategies. Let's look at 3 of the most common hiking styles. Let's start with the 2 extremes. On one side, you have batch gradient descent. Think of this as the cautious planner. This hiker looks at the entire landscape, every single data point, to calculate the absolute perfect, most accurate direction for one single step. It's very stable, but with a big data set, it's painfully slow. Then you have the complete opposite, stochastic gradient descent, or SGD. This is our impulsive explorer. This hiker takes a quick look at just one random data point and immediately takes a step based on that. It's way faster, and its zigzagging path can sometimes help it escape tricky spots, but the journey is really noisy and chaotic. So you have the slow and steady planner versus the fast and wild explorer. which naturally makes you wonder, is there a middle ground here? Can we get the speed of one with the stability of the other?
And the answer is a resounding yes. That's mini-batch gradient descent, and honestly, it's the approach used in pretty much all modern deep learning. Instead of looking at all the data, or just one piece of it, it looks at a small, manageable group, a mini-batch, say 32 or 64 data points at a time. It calculates its step based on that small sample, and this gives it a beautiful balance between the speed of SGD and the stability of batch GD.
So what does this mean in practice? Well, this table gives you a pretty good cheat sheet. If you've got a tiny data set where speed doesn't matter, batch GD is fine. If your data set is absolutely massive, sometimes SGD is the practical choice. But for most deep learning tasks, mini-batch is the undisputed champ. It gives you that perfect balance of speed and reliable progress. All right, so as we come to the end of our hike, let's just make sure we've got our key takeaways packed up. We've seen that machine learning is really just a process of minimizing mistakes, and gradient descent is our trusty guide for finding the path to the smallest possible mistake. If you ever need to explain this in an interview, this is your go-to definition right here. It's an algorithm that tweaks a model's settings over and over again, always moving in the direction that makes the loss, that wrongness score, go down the fastest. It's simple, it's elegant, and it's incredibly powerful. And remember, our three main flavors. Batch GD is your stable but slow workhorse. SGD is the fast but chaotic option. And mini-batch GD is that best of both worlds approach that really makes modern AI possible. And that's gradient descent. This one simple idea, taking small steps downhill, is what allows machines to do everything from recognizing your face in a photo to translating languages on the fly. So I'll leave you with this. Now that you understand the fundamental way a machine actually learns, what's the very first problem you'd want to teach one